So this is the final iterative method that we're going to consider in MEC MAE 3456, and it's known as successive over-relaxation. Successive over-relaxation basically starts with the Gauss-Seidel method that we looked at in the last recording. So that's just repeated up here, the equation that's repeated here. What we're going to do with this equation is we're going to do something that seems a little bit strange at first sight. What we're going to do is we're going to add the current guess for our solution, the xim, and we're going to subtract it. So in other words, we're not adding anything of substance to this. But what we're going to do is we're going to move this one up here, and we're going to put this one, or we're going to, I should say, we're going to group this one with the term in the brackets there. So this then looks like this. xim plus 1, the new guess, the new iterate, is equal to the old iterate, plus this thing here, and that is just the normal Gauss-Seidel iteration, but we're going to subtract from it our current guess. So we haven't done anything except add a couple of terms and rearrange the equation. So far everything looks pretty much exactly the same as Gauss-Seidel. Now, however, what we're going to do is we're going to introduce a parameter that's called the relaxation parameter. And that is, we're going to denote that with omega. And so what we're now going to do is we're going to take all of this term, and instead of just adding it directly onto xim, we're going to multiply it by omega before we add it on. So we're actually changing things just a little bit. So just have a look at this. New iteration is equal to the old iteration plus omega times this thing here. Okay, so this expression that we've got here at the bottom of the page is equivalent to the following. It's equivalent to calculating the Gauss-Seidel iteration. So I'm just going to call the Gauss-Seidel iteration for the purposes of this small description here as xim plus 1 tilde. So we know that that's what we would get for xim plus 1 if we used Gauss-Seidel. Okay, so denoting that as that, we can see that the new value of xim plus 1 is equal to omega times the Gauss-Seidel iteration plus 1 minus omega times the old guess. So what we've done effectively is we've calculated something with Gauss-Seidel, we've weighted it by omega, and we've added on a different amount of our current guess. And the amount that we've added on is 1 minus omega times the current guess. Now, it turns out that the relaxation parameter omega must take values between 0 and 2. So if omega is equal to 1, it turns out that we get Gauss-Seidel straight back. So if omega is equal to 1, this term here disappears, that omega is 1, and we just see that xim plus 1 is equal to xi tilde m plus 1, which is just the Gauss-Seidel iteration. If omega is less than 1, we have what's known as under-relaxation. We won't really need to use under-relaxation in this course, but keep it in your toolbox there, because sometimes it's good to try when Gauss-Seidel fails to converge or indeed diverges. So there are some cases where under-relaxation can be very useful. For omega is greater than 1, we have over-relaxation, and that's really what we're going to be considering in this unit. So effectively what we're saying is extra weight is put on the latest iteration, and we're going to discount the previous guess a little bit. And successive over-relaxation often converges much faster than Gauss-Seidel, really significantly faster. There is an optimum value of omega, which depends on the problem, and you can't normally figure out what this optimum value is in advance. Let's have a bit of a look at how we can try and estimate it, however. Okay, so SOR converges quickly for an optimal value, and because we're talking about over-relaxation, 1 has to be less than this optimum value, which has got to be less than 2. We can find it by trial and error or some kind of iterative improvement. But it turns out that the optimal relaxation factor can be related to the spectral radius of the Gauss-Seidel iteration matrix. I'm not going to go in and describe what that means. It's not really important for this unit. So if we can calculate the spectral radius, lambda max, the optimal relaxation parameter is given by this expression here. 2 divided by 1 plus the square root of 1 minus the absolute value of the spectral radius. So if we can find some way of calculating this, we can then estimate the optimal relaxation parameter. It turns out that there's a really sort of simple way to estimate the spectral radius, and it's called the power method. So in practice, what you can do is you can estimate the spectral radius, lambda max, using this expression here. So this vector here is our guess to the solution at iteration n plus 2. This is our guess to our solution at iteration n plus 1, and this one here is our guess to the solution at n. Okay, so we need 3 different iterations of this to be able to use it. So what we then do is we calculate xn plus 2, subtract xn plus 1, and we look at the magnitude of this. It's a vector. We can figure out what the size is. And then we divide it by the magnitude of xn plus 1 minus xn. So these are just 2 numbers, and it gives us an estimate for the spectral radius. So these straight lines here and here is a measure of the size of the vector, and it's called a norm, and there's a whole bunch of different norms that you can have. Typically, the most commonly used norm is known as the L2 norm, which is the Euclidean vector norm, and it's given by this modulus here is equal to the square root of the sum of the squares of the vector. So this thing here is summed up over each of the components, and then we take the square, or squared, and then we take the square root. That tells us how long this vector is. And so if we do this with each of these pairs of iterations, we can come up with an estimate of lambda max, and then we can go back and substitute that into our expression for the optimal value of the relaxation parameter. So a possible strategy for actually doing this in practice is to do 2, probably 3 iterations of the Gauss-Seidel method. In other words, use omega equals 1, use these to estimate the spectral radius, use the spectral radius to estimate the optimal value of omega, and then use this value of omega here as a new relaxation parameter. Or you could probably think of coming up with some strategy that was similar, that you could modify the optimal parameter as you went along. So to summarize everything that we've looked at in terms of iterative solutions, that's Jacobi, Gauss-Seidel, and successive over-relaxation, iterative methods have the following benefits. They only require us to store the non-zero elements of the coefficient matrix A. Okay, and this really can significantly reduce the memory requirements of the problem. They can be faster, and often very much faster, than determining the inverse of a very large matrix. However, iterative methods also have some problems. They may diverge, or they may take a really significant time to converge to an acceptable answer. And that's certainly true of the Jacobi method.